Welcome to Designing with Hall Effect Sensors. In this video, you will learn about obstacle avoidance in robotic applications. Autonomous robots, such as robotic vacuum cleaners, must include mechanisms that allow them to avoid obstacles in areas that the user would not want the robot to approach. Such function is commonly referred to as obstacle avoidance. Obstacle avoidance can be implemented by attaching Hall effect sensors to the base of the unit in order to detect a magnetic strip. The magnetic strip is applied by the user around regions or obstacles they would not like the robot to converge on. The Hall effect sensors allow the robot to sense the magnetic flux density emitting from the magnetic strip as it passes by. If there's no magnetic flux detected, then the robot can continue on its predetermined path, but if the robot detects the magnetic strip, it can be configured to turn around and avoid the area. Autonomous robots are meant to operate and perform all their functions off of battery, so it is imperative that the devices used to monitor the magnetic strip offer low power consumption to reduce battery drain. The sampling frequency of the Hall effect sensor can be a driving factor to the amount of power consumed, but it is also vital to ensure that the sampling rate is suitable for the speed of the robot. For example, if the sampling frequency of the robot is too slow in comparison to the robot's speed, there is a possibility the device might miss the detection of an event. Lastly, the system must be robust and reliable in all kinds of work environment, such as areas where the device is prone to be introduced to dirt and debris. Our magnetic sensing portfolio provides many options when designing for magnetic strip detection. The TMAG5231 is a family of low-power Hall effect switches. These devices offer various sampling rates as well as several threshold options depending on the application. The TMAG5231 is offered in both SOT23 and X2SON packages to enable small form factor solutions. The TMAG5328 is a low-power Hall effect switch that offers magnetic threshold configuration via an external resistor or an external voltage. The device's thresholds can be configured anywhere between 2 millitesla to 15 millitesla. The TMAG5328 operates at a 20 Hz sample rate with a 1.4 microamp average ICC current to help conserve power in battery-powered applications. The magnetic strip used for obstacle avoidance works just as a normal magnetic rectangular block would, but unlike typical magnets, they are available in large rolls that can span up to several meters long. In order to quantify the strength of the magnetic field generated by the magnetic strip, a Lakeshore F71 Teslameter was used. Since the obstacle avoidance board being developed will be fitted into a TI RSLK kit, the field generated by the magnetic strip was measured in reference to the height of the robotic kit and the PCB. The field perceived in the z-axis at approximately 1.5 centimeters had a max value of 5.8 millitesla across its entire length of the magnetic strip, enabling us to use the TMAG5231 B1 variant with a magnetic threshold of 2.85 millitesla. The TMAG5328 was set with an external resistor of 2.8 kiloohms in order to adjust the BOP to a threshold of 2.84 millitesla. Here we have the completed board fitted with both TMAG5231 and TMAG5328 devices. The obstacle avoidance board contains footprints to include up to 8 Hall effect sensors, but please note that all the devices pictured are not necessary in order to detect the magnetic strip. Typically, only the robot's extremities need to include Hall sensors. Outfitting the extremities with a sensor will help ensure that the robot detects the magnetic strip as soon as possible, allowing it to perform any preventative action before causing any damage. The board has been attached onto the bottom of the TI RSLK module. The TI RSLK module uses a CC2652R1 launchpad module to control all of the functions on the robot, as well as communicating its status wirelessly to another CC2652R1 launchpad, connected directly to the PC. The additional microcontroller allows us to print the status of the robot to the terminal, while also enabling the use of a magnetic joystick to control the speed of the motors. The TI RSLK is surrounded on 4 sides by the magnetic strip. If the obstacle avoidance board detects a magnetic field from the magnetic strip, the robot is programmed to reverse and rotate approximately 90 degrees. The robot will then continue its path forward unless if another magnetic strip is detected. This concludes our demonstration and video on designing with Hall effect sensors. If you'd like to learn more about this topic, please refer to these articles and visit ti.com/Hall effect for more resources and tools. Thanks for watching!